Ithaca, New York, without any teaching obligations. Ms. Dani spent the spring of 2017 semester at the SAID Cornell University, where she worked with Team Relay and interacted with the other faculties of Cornell University. Ms. Dani's research has been supported by grants from the National Science Foundation. She received a Simmons Foundation collaboration grant to support her research from 2016 to 2018. So this was a small introduction, so a small mythography of Ms. Dani. Now I invite Ms. Pallavi Dani for the lecture.
Okay, thanks very much for that kind introduction. So it's a real honor for me to be speaking to you all and on the occasion of the International Women's Day. And I'd like to tell you a little bit about the kind of math that I do. The title of my talk is Stallings Folds, a Topological Approach to Free Groups and Beyond. So I'm going to start with some sort of classical stuff about free groups, starting with just reminding you of what a free group is. And then I will, later on in the talk, I will talk about some recent developments, so my own research, and that is all joined with Ivan Levkovitz, who's a postdoc at Tufts University right now. Okay, so please feel free to ask me questions in case there's something that's not clear. Okay, so let me begin with free groups. So when I talk about a free group, some of you may be more familiar with free abelian groups, but that's not what I mean. So I mean a free non-abelian group that's finitely generated. So F is my free group, finitely generated free non-abelian group. And as an example, you could take the free group generated by A and B. So the elements of this group are simply freely reduced words in A and B. So what do I mean by a word? I just mean literally just write either A's and B's or their inverses. So, and maybe powers as well. So this is an example of a word. So consider the set of all such words, and then a word is freely reduced. I'm not giving the formal definition, but I'm just sort of explaining it by example. So freely reduced means it has no instances of A directly followed by A inverse, or B directly followed by B inverse, or A inverse A, or B inverse B. So for example, the following is freely reduced. So if I take A, B, A inverse, that is freely reduced, but not A, B, A inverse A, because this prevents it from being freely reduced. Okay, so, right, so the elements are freely reduced words, and to multiply two elements together, we simply concatenate them. So that means if I have two elements, say A, B, A inverse, and maybe A, B to the 7, then the product of these two is what you get by simply putting them together. But as you can see, sometimes when you put them together, you end up with something that's not freely reduced. So this is the concatenated part. This is the concatenation of this and this, but it's not freely reduced. And so now we freely reduce it. So cancel A and A inverse, and we get the freely reduced form of this word. And I can combine this B with this to get AB to the 8. And so this is now again of the same form, freely reduced word in A and B. And so that's my multiplication. That's the product of this element and this element. Okay, so that's, all right. So we have this set of elements, freely reduced words in A and B, including the empty word. And we've defined this multiplication, and it's not hard to check that under this multiplication operation, this forms a group, and this is the group that we're talking about. So this is a free group on A and B is what this is called. Okay, so these are the objects that we're talking about. Later on, we're actually going to be talking about subgroups of these objects. But let me introduce two notions that are related to this, this group, which is a basis and the rank. So the basis for F is just a minimal generating set. Okay, so if F is our free group on AB, then a basis, in this case, it's easy to see that the basis, a possible basis is just A and B. But that's not the only possible generating set. You can also get the same group by, say, considering A and AB, because so it's an easy exercise in group theory to show that the group generated by AB is the same as the group generated by A and AB, or it's the same as the group generated by, say, AB and AB squared, etc. So there are infinitely many possible bases that you could write down. In fact, any pair of elements that generates the group is a basis, because here 2 is the minimal number of elements you need to generate the whole group. And then in this case, the rank is just the number of elements in the basis. And so it's just 2. Now, you might think, well, this is kind of a silly concept because I've written this as free group in AB, so it's obvious what the rank is. However, a free group might show up in contexts other than the way we've defined it. So, and so here's another group. Now, this group is going to be given in terms of a presentation. So when I write this kind of thing, this is a presentation. Now, this is a standard way of defining an infinite group or even a finite group. So over here, what we have are the generators. So the group is generated by 3 elements, A, B, and C. And on the other side of this bar, we have relations between the generators. So we have a collection of equations that hold in this group. Now, when you have a free group on AB, you don't have any relations. It's just the generators and then the elements of the products of the generators. But for more general groups, there are going to be some relations between the elements. Now, it turns out that in this case, this looks like a group that's not free because it has relations. However, on closer inspection, you can see that this C is kind of a redundant generator because I added this C and then I just said C is equal to this word on AB. And so I could have just folds and we ended up with this final thing, which is folded. So now I claim that this graph at the end can detect the rank of the free group H, and we can use it to find a basis for the free group. So first of all, one thing to note is that whenever you have a graph, you can think of that as a topological space, and the fundamental group of this graph is always a free group. And the way that you figure out the rank of that free group is by selecting a maximal tree. So actually, let me choose a different color. So selecting a maximal tree. So a tree is something with is just a graph without any loops. So a maximal tree is one which includes all the vertices. So in this case, this is an example of a maximal tree. And so now I've just got the green tree, which has all of the vertices, and then I have three edges left over, which are not in the maximal tree. And then that means that the rank of this group, the fundamental group of this graph, is 3. But what does this have to do with our subgroup H? Well, it turns out that you can consider this very elementary rows where the petals are simply A and B. And in this case, this is a space whose fundamental group is actually the free group on AB. And whenever we draw a picture like this, what this is actually telling us is it's actually giving us a map from this space into this space. So there are actually maps from each of these spaces into this space. So for example, what does it mean? What does this map do on this particular loop? Well, this particular loop goes A, B inverse, B inverse. So that means that you take this loop and you wrap it around A, and then you wrap it around B inverse, and then B inverse again. And so for each of these loops, these labels just give instructions on how to map it into this space. Okay, so we have this sequence of maps, and the important thing about this last one is that because this last one is folded, it turns out to be, this map turns out to be what's called an immersion. And that means that the map from the fundamental group to the free group on AB is injective. So we started with this picture, and the map which sends this picture into this picture sends the group H. So the image of the fundamental group of this picture over here is exactly the group H.
Now, what is basis of H?
So right, we're getting to that. That's the next thing I'm going to talk about. So right, so the image of the the image in each case, so there's a topological space here, it maps to the topological space here. This means that there's an induced map for the fundamental group of this into the fundamental group of this. And so the image of that map is H, okay? And so this tells me that this group, the fundamental group of this, is actually equal to or isomorphic to H. And so now that I know that that this is actually a group isomorphic to H, I can use this to find the basis for H. So what I do is, I know that the basis is going to have 3 elements, and this used to be my base point. And so I just go, the basis is going to be in one-to-one correspondence with these 3 edges that are not in the tree. And so I can sort of go along this loop. Whoops. I can go along this loop. That's 1. And then this loop, that's another, and go along this loop, and that's a 3rd. Okay, so I can write down what these things are. So going along this one, I get A, AB squared. Then going along this one is A, B, A inverse, B, A inverse. And then finally, this one would be A, B inverse, B inverse. Okay, so maybe I should erase this so that it's easier to see. Okay, so this maximal tree that we chose gave us a way to choose the bases. And the reason this works is this business with these maps that, that I was talking about. Okay, so notice that when we first started, H had 4 generators, but it turned out that one of those generators was redundant, and this sort of was captured by this folding process. So the folding process took care of this redundant generator without having to manually look for redundancies in the generating set purely combinatorially. Okay. So, so this is how you solve the rank and basis problem for a free group using foldings. Now, let me tell you about the index of H and F. Now, it turns out that the index of the subgroup H can also be computed very simply from this lambda H, from this folded graph that you get from H. To determine the property that you need, we have to make a definition. And the definition is what I'm going to call full valence. So one of these graphs is full valence if every vertex has an incoming and an outgoing edge corresponding to every generator, right? So over here, you can see that this vertex has no incoming A. So this is not full valence. But these other 2 graphs have this property. So if you, I'm not going to go through all of them right now, but if you pick any vertex in this graph, then there's an outgoing A and an incoming A, and an outgoing B and an incoming B. And so both of these have this property. They're both full valence. Okay, so both of these graphs are full valence. And this property is what tells us what's going to tell us whether the subgroup that they correspond to is of finite index or not. And it turns out that it's finite index if and only if the graph has full valence. So unfortunately, the stuff I wrote on the previous slide is gone, but this one was not, and this one was, and this one was. And so in order to find the index of these subgroups, you just have to count the vertices. So here we have 1, 2, 3, 4, 5. So that's 5 vertices. So the index is 5. And here you have 1, 2, 3, 4. So the index is 4. Now, again, this might look a little bit mysterious, but there's sort of a very nice topological explanation for why this is actually the correct way to find index. And the reason is, again, going back to these maps that I was talking about from our graphs to the basic graph, which is the rows with 2 petals. So we already said that if you have, you always get a map from graph to this rows on A and B. But it turns out that if this is actually full valence, then in fact, this is a covering map. Now, covering maps are very special maps in topology. And there's the fundamental theorem of covering spaces tells you that there's a correspondence between subgroups of the fundamental group of this space and covering spaces of the space. So, and then the degree of the cover, so the number of vertices in this case, which all map to this one vertex, this degree of the cover is actually equal to the index of the subgroup that it corresponds to here. So if you're not familiar with covering space theory, then perhaps that was a little bit too quick. But in that case, just know that there's sort of this topological theory of covering spaces, and the fact that all you need to do is to count these vertices comes from applying that theory. And so a lot, the sort of hard work is done in that theory, and now we can just reap the benefits and know that to find the index of our subgroup, all we have to do is count. All we have to do is check whether this property of full valence is satisfied, and then count the vertices. Okay, so any questions? Okay, so I've explained how to do a few of the problems that I mentioned before. So rank and basis and finite index. These other problems, which I did mention, but so these other problems, I did mention them. I'm not going to go into the actual solutions of these problems, but there exist solutions that are along similar lines of the ones that I talked to for the first three examples. So you can solve a bunch of these combinatorial problems for free groups in this way. And in fact, you can do a lot more than what I already mentioned. I picked the ones that were sort of easy to state, but there's actually a lot more that you can do. And in fact, these types of foldings are still very much present in the study of free groups, as well as automorphisms of free groups. Okay, but like I said, I did want to spend a little bit of time talking about some more general situations. And so let me say that these things have been adapted to many other settings, but there's one thing that makes this much trickier than free groups, which is this thing that I mentioned before, that any group which is not free must have relations in the presentation. So you have generators, but you also have relations between the generators. And these relations give you elements that are products of generators, but they represent the trivial element of the group. And these lead to problems. So I just wanted to put down a list of some of the situations where these things have been generalized to, but the thing that I really want to focus on is this case of what are called right-angled Coxeter groups. So it's okay if you haven't heard of the groups that are on this slide, because this is just sort of to indicate that this has been generalized to many settings. And it's also okay if you haven't heard of right-angled Coxeter groups, because I'm about to define them, and they have a very nice and simple definition. So, okay, so a right-angled Coxeter group is defined in terms of a defining graph, which is a finite simplicial graph. So a graph has some vertices and some edges, and that is used to give a presentation for a group. So the generators of the group are the vertices, and you just have the relation that the elements commute exactly when there's an edge between the corresponding vertices, and every generator has order 2. So it's probably a good idea to see some easy examples. So if the graph is just simply 2 vertices, then all you get is z mod 2z corresponding to this vertex, a z mod 2z corresponding to this vertex, and then they don't commute with each other, and so you get the free product of these 2 groups, just a free product of these 2 groups. And the notation that we use for this group is d infinity. Okay, now if you do have 2 vertices, but there's an edge between them, then you still get 2 z mod 2z's, but they commute with each other because of this condition, that whenever you have an edge between 2 vertices, then the corresponding generators commute. Okay, and then if you have a square, then this element and this element, that's similar to this situation, and that gives you a D infinity. And similarly, this element and this element gives you a D infinity. But notice that both of these are connected by edges to both of these. And so this D infinity commutes with this D infinity. And so you get D infinity cross D infinity. Okay, so these are just some specific examples of right-angled Coxeter groups. As you can see, that it's a very elementary definition. And it turns so it might surprise you to learn that there's actually a lot of interesting mathematics that that you can see in this family of groups. And so I should also say that in all of these examples, I was able to just give a decomposition into some easy pieces. But if you, for a general right-angled Coxeter group, it's not really fruitful to kind of try to decompose it in this way. You just think of it in terms of the graph that defines the right-angled Coxeter group. Okay, and so our goal was to come up with a theory of Stallings foldings for this type of class, this type of group. Now it turns out that instead of graphs, the correct object to look at in this situation is not graphs, but these certain things called cube complexes. So these are, instead of graphs, it's the higher dimensional generalization of a graph. So in a graph, you just have vertices and edges, right? But now in cube complexes, you've got vertices, you've got edges, and then you've got the two-dimensional analog of an edge, which is a face of dimension 2 or a square. And then this thing that looks like a cylinder is actually also, it's a square that has two of its sides. That's an analog of a loop which has its two ends identified. And then here, this thing right here is a three-dimensional cube. So you've got cubes of all these dimensions. And the objects that we're going to consider are these labeled cube complexes. And so, right. So this time we want to consider things that are gamma labeled. So it has a label for each vertex of gamma, or each edge is labeled by a vertex of gamma. Opposite edges and squares have the same label. Oh, and this time the edges are unoriented because that has to do with the fact that these generators are all going to be of order 2, and so we don't want orientations on them. Okay, and then whenever you see a picture like this inside the graph, then that means that whenever you see a cube with labels, and you have a single vertex with an A and a B and a C coming out of it, then that means that in the graph, there must be a triangle whose vertices are A, B, and C. Okay, so these are the conditions on the cube complexes. And now we have 3 different types of fold operations that we can perform to these types of complexes. So the first thing is just the same thing that we had before. Namely, anytime you see this picture, you can fold it to this picture. But now we have some extra types of moves that we can do because we're not in a graph situation anymore. So the first one is just a higher dimensional analog of a fold operation. So supposing you had a square, and then you had two different squares whose boundary is the same, two cells whose boundary is the same square. So this thing is, here's a square, and then there's actually, it's sort of like a pillowcase. There's a front square and a back square. And that just gets identified to a single square. So this is, this can be done for cubes of any dimension. So if you have multiple cubes with the same boundary, just identify them to the same cube. And finally is a cube attachment operation. So this time, if you see this picture, if you see a picture like this, where you have a vertex with three edges coming out of it, and you know that the labels of these three vertices commute, then you must attach a cube to this picture. So you can see that the situation becomes a little bit more complicated than what we had in the free group situation. And now we need to know that, we have the same notion of folded, just like in the free groups situation. And then we have a notion called cube full. So you need to know, how do you know when to stop attaching? Situation where, say, as in this picture, where you have in your graph, you've got A and B, and they are connected by an edge. And then in your complex, you see a vertex with an A and B. Then you must, because these two things commute in the graph, you must actually attach a cube cell, two cell here. And so once you've attached this two cell, then it becomes cubeful. But before you attach it, it's not cubeful. Until you've attached this cube cell, this two cell, it's not cubeful. Okay, so we have these two different ways to tell whether we are done or not. And now we can start performing these folds just like we did in the previous case. And so if you start with a finite gamma labeled complex, then you can consider a sequence of folds, cube identifications, and cube attachments. And then you can form, so unlike in the free group situation, this might not be a finite sequence, unfortunately. It would be, in general, it would be an infinite sequence. But you can still form this limiting complex of this whole sequence. And this is the analog of the lambda h's that we had before. So if you take this limit and you find that you get a cubeful and folded complex, then you get what we call a completion of X. And just like in the free group setting, this is going to capture a lot of information about free groups. So just like in the free group setting, if you take a subgroup of the right angled Coxeter group, then you can start with a Rose graph with whose petals are labeled by the generators of the subgroup, and then you perform these sequence of moves, you get a completion, and that completion captures a bunch of information about the group. And so, just to give you an example, if your graph is this graph right here, then and your group is generated by these two things, then your Rose graph that you start with is a space like this because there are two generators. And so you take the two generators and you label it with the words. And then you get a sequence of moves, which gives you the completion. Okay, so the first thing you do is you fold these two red edges to a single edge. And then you see that this vertex here corresponds to right. So if you have these vertices correspond to these vertices correspond to a triangle, and so you attach a cube, and then you're done. So now it turns out that this terminal object carries information about the group. And let me just give a contrasting example here, where in this situation, unlike in the free groups case, this is a situation where you're going to end up with an infinite sequence of elements, infinite sequence of spaces. And when you do the completion, you actually get an infinite cylinder. So this is contrasting with the free group setting. So these objects that we've constructed capture all the properties that we were talking about for free groups, which I won't talk about, what exactly the conditions are, but hopefully I've given you a flavor of what this generalization looks like in the right-angled Coxeter group setting. And I'll stop there.
Is there any query from students?
Is there any question or query from the YouTube livers?
Pallavi ma'am.
Yeah.
It seems that there are no questions from the students. So being a layman, I want to ask you, please justify the word free in the definition of free groups. And why they are called free?
So it's free in the sense of free of any relations, basically. That's my understanding, that free means that there's no extra conditions on the group. It's just the generators determine everything. So for example, a free abelian group is you have the generators, and then you have the abelian tells you that you get commuting relations, but free means that there's no extra conditions or extra relations on the generators.
Okay, thank you. So thank you very much, ma'am, Pallavi ma'am, for actually our students, our MSc students, they are familiar with how to use number theory in group theory, just like Wilson's theorems and whatnot. But this geometric group theory, certainly it is a new topic for them. And I believe that our textbooks should actually introduce some basic examples. Our textbook actually does not contain any such examples. Basic. So
do they do free groups at all?
No, in our syllabus, we do not cover this topic in MSc syllabus.
What about covering spaces?
I think that is covering spaces are also not covered. But some teachers give some examples, but actually it is not in the syllabus.
Yeah.
Okay, so thank you very much for interesting and lucid lecture. And
okay, well, thank you for your attention.
Thank you, Dr. Pallavi Dani, for accepting invitation and giving away your slip for almost 2 hours. So thank you very much. And hope we will be in touch, and in future we may meet physically.
Yeah, I hope so.
Yeah, Gujarat is a very beautiful place. Madam,
yeah, I think I came there once when I was very young, but not recently.
No, now it is very beautiful place. Madam, you will have to make me host so that I can stop recording and download it.
Oh, how do I do that? I think you should still be the host.
No, no.
Okay. Okay, well, I can...
Recording stopped.
How do I make you the host?
Okay, you can stop recording. That will also take care.